Okay, if I would just record some different problems from section 1.5, just to have some more on there if you needed them. If you look at the directions there, we're supposed to, the ones I assigned were 1 through 5 odd, so that's what we'll look at. On number 1, it says determine whether the function f of x approaches infinity or negative infinity as x approaches negative 2 from the left and from the right. Well, here's negative 2 right here. So this is, we've got an asymptote here. And from the left, as x approaches negative 2 from the left, we see that it's going up. So from the left, it's approaching infinity. And then from the right, it's also coming in and going up, so it's approaching infinity. We'll look at number 3, just since I've got the picture on here. For the tangent curve, we're particularly just looking again at where it's approaching negative 2. It's right here. And I took the picture at an angle, so it's kind of hard to... a straight line is actually not straight up and down here. There's an asymptote there. There's no value for tangent on multiples of pi fourths. Okay? And so if you look at the left of it's going to infinity, it's because it's going up, right? But on the right, as it approaches negative 2 from the right, it's approaching negative infinity. If you notice on problems like number 3, this one, it's not continuous anyway because of the asymptote, but we would have to just talk about the limit from the left. The limit is x approaches negative 2 from the left being one thing and from the right being another, just because there's no way to talk about, besides the fact that it's not continuous, the limit as we approach that value is two different things, one different thing from the left and the right. So that's one thing that this is one of the reasons that we use this notation of approaching things from the left and right, is to deal with situations like this. Okay, for problems like 9 through 27, where we're looking for vertical asymptotes of a graph, if you remember back from Algebra 2 and pre-calculus, one of the things that we know about finding vertical asymptote, it's where the denominator is equal to 0. So denominator equals 0. In this case, our denominator is x squared, so where is x squared equal to 0? We solve for x. Oh, x is 0. So we have a vertical asymptote at x is 0. I'll pick another one. Let's look at 27. It's just interesting because it's a trig function. I don't even know if I assigned it or not, but if I didn't, that's okay, because we need to be able to do the ones with trig functions on them. Okay, so t over sine t. So again, where's the denominator equal to 0? Where is sine t equal to 0? Well, in order to think about that, what we'd want to do is draw our unit circle again, because if you remember, the sine value, if you have your point on the unit circle, xy, the x is the cosine of the angle that you're looking at, and the y is the sine of the angle that you're looking at. So if I can find where the y value is 0, that would be where sine was 0. I could solve this problem really quickly without having to look at a graph. Well, the y is 0 here and here. So what angles are those? That is at t equals 0. I'll just say we're working in radians here. And then over here, if you remember, that's pi radians. Or you could, in degrees, that would be 0 degrees and 180 degrees. 25 is an interesting one because you have to factor it. And in case you don't remember how to factor by grouping, I just thought I would pick this one because it would be a good one for us to look at to just review factoring by grouping, which we did in Algebra 2 and Pre-Cal. I'm trying to remember what class I'm in right now. All right, so if I'm going to actually go factor the bottom first. If you remember factoring by grouping, what we did is we came in and we looked at pairs of terms. Okay, and I see that this x minus 5 is on the end here, so I'm thinking I probably can get an x minus 5 out of this first pair of values. So I'm going to say, okay, let's see, what is the common factor in x cubed minus 5x squared, that first set of terms on the bottom? Well, they both have an x squared in them. And when I take the x squared out of those two terms, what I have left is an x, and then a subtraction sign, and a 5. And then I have a plus x minus 5. I'm going to keep factoring the bottom just because, it's helpful to kind of keep that track going. Now, I'm going to put a visible 1 there so that I can remember how to handle this. If I see in the denominator that I have x minus 5 in both terms, I'm going to factor that common term x minus 5 out. And then what do I have left? I have left x squared out of the first term, and out of the second term here I have 1, so x squared plus 1. Now let's go factor that top term. Okay, what multiplies to give me negative 15 at the same time adds up to negative 2. Let's see, it would be a 3 and a 5. I want more negatives than positives, so I'll put the negative on the 5 and the positive on the 3. And that would factor that top part, so let me copy that down here. X plus 3, x minus 5. Okay, now, if I'm trying to determine where the asymptotes are, I know that if I have a factor that cancels out, that's actually a hole in the graph, which is called a removable discontinuity, which would mean I could look at the function as being continuous at that point and just kind of ignore the fact that there's a hole there in the graph. It would still have a limit even though that point doesn't have a value. It would be an error if you looked in the calculator. Now, what about asymptotes? The asymptotes come from other places in the denominator that equal to 0. So let's come over here and put x squared plus 1 equals 0. Okay, now if we look at this, x squared is negative 1. Ooh, if we take the square root of that, that's an imaginary number. So there are no asymptotes here. So the only thing we have here is a removable discontinuity. I thought I would pick 41 to look at just so we can talk about a couple of ideas that are in this chapter. One of the things that we look at when we look at taking the limit of this is we got two functions added together. And so if you look on page 87 in your textbook, you see that I can look at these limits separately. The limit of 1 as x approaches 0, that's like saying, this number right here is saying you have a function of y equal 1, which is a horizontal line. So on a horizontal line, if you were looking at taking the limit at 0, it's still going to have a value of 1. All values, y values on a horizontal line would be the same, and it would be 1. So that limit would be 1. So now, the reason I'm pointing this out on page 41, it says if we have two functions added together, then if one of we can basically, we know we can add those limits together, but in this case what's going to happen, let me just write the separate limit thing for the second one. As I'm approaching 0 from the left hand side, I'm putting in values close to 0. Can't put 0 in because of you can't have this undefined fraction, but what's happening, I'm getting a lot of very, 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 very small negative numbers. And 1 divided by, let's say, negative 0.000000000000001 would be a very large negative number. So what I would say is this would be 1 plus negative infinity, because your x's are coming from your left hand side, so they're negative. So from page 87, when you add those together and you have one that's infinity, it just ends up, or negative infinity, it ends up being the negative infinity, because negative infinity plus 1, that 1 is really inconsequential when you kind of think about the negative infinity. So that would be your limit there. And on number 43, if we think about the limit as x approaches infinity from a negative direction, that x approaches 0 from a negative direction, of 2 over sine x, if we look at 0, sine x, sine of 0 would be the y value, here's the point at 0 degrees or 0 radians, whatever you want to say. And if I take the sine value of that, that's the y value here. The y value is 0. So sine of x is approaching 0. And so we can see we're getting infinity. What we need to think about, is it negative infinity or positive infinity? in order to think about this, let's kind of think about what does sine look like. The sine function is, if you start at 0, it kind of goes up, and, it's doing this, so it's going to be going like this in the other direction. This is why it's important to be able to sketch these quickly. You don't want to have to think too hard about this. As I'm coming up to 0 from the left, these are negative values here, and I can get very small negative values because this is getting close to 0, so I could pick, again, like I did on 41, negative 0.000000001, or however many zeros you want to stick in there. So it's actually approaching negative infinity. So thinking about the graph actually helps me about this because it's talking about this area right here. It would be 2 over very small negative numbers. Since we can't plug in 0, we could think about doing this. And so it would end up being negative infinity for 43. So I kind of use the idea of the unit circle to help me remember that the sign of 0 is 0. And then I used the actual graph of it to help me realize, oh, that's coming at it with negative numbers there, so I really got to think I'm plugging in something like this if I wanted to direct substitute, I could do it, and I could see this would be negative infinity.